going to introduce a very powerful mathematical object called a tensor that we're going to use to explain, Einstein's general relativity field equations, and other things too. So that's fascinating.
As said before, tensors are a mathematical object, very powerful. I mean, we'll see that in another video about general relativity. They basically represent linear behaviors. To show you their power, I'll give you some example of tensors. Numbers are tensors, vectors are tensors, matrices, linear maps, and a bunch of other mathematical objects can be represented with tensors. So as you can see, it's very powerful. There are several definitions for tensors. One I like is that given a vector space V defined on a field K, PK tensors are multilinear forms from this to K, okay? In other words, they take elements from the dual space of a vector space and combine them with element of the vector space. In other words, vectors give you a scalar. Now, why do you want to use tensors? Well, again, they're very powerful objects, and also they basically have linear properties. And the universe follows a lot of linear rules. Not all the rules in physics are linear, but a lot of important ones are. And tensors allow to hide the actual complexity of structures and systems of equations. This is a tensor, here, and given a basis, its value is actually this big matrix here. And this is for a 2D vector space, So imagine what it could look like for vector space with 3, 4, or even an infinite number of dimensions. That gives you an idea of why tensors are useful. They're also pretty easy to work on. Well, they have simple rules to manage their indices. And, tensors can have many indices. And here are some examples, for instance, here, if you have two tensors with the same indices, upstairs and downstairs here, well, you can combine them like this for an addition. And the tensor product here, you can manage pretty easily the indices like this. And here, well, for instance, where you have the same index upstairs and downstairs, well, you can simplify that and write it like this. So there are a lot of rules like this which allow to simplify tensor equations. And the next thing is they are universal. So what does that mean? Well, that means they work for all frame of references, In other words, it's like abstract vectors, which are valid everywhere. Well, the same thing here happens for tensors. And by the way, vectors are tensors, so that's not very surprising. And we'll use that, of course, a lot. Now, one of the simplest example of tensor, which can be useful because scalars or numbers are tensors, but it's not very useful for what we want to show here, is a vector. A vector is a simple yet representative example of tensor. We'll explain in details why a vector is a tensor in a few minutes. But here I want to insist on the fact that there are, vectors which are abstract vectors and others which are definite vectors. Actually, they're the same, or at least they represent the same object. But in the case of an abstract vector, it's just an element of a vector space defined over a field F of scalars. And only once you have defined a basis, then it can become a definite vector with some values here, and then you can write it this way. The definite vector representation here, again, is only valid for that particular basis here, okay? And if you change the basis, of course, the definite vector representation will change, although it represents the same object. Now, then, once you know that, how do you use vectors in equations, theorems, etc.? Well, first, what you do is you use abstract vectors, and you do all the calculation you have to do using those abstract vectors. You don't worry about the basis. You don't worry about their coordinates or components, whatever you call them. And then, once you are done and you have simplified your your equations here, then you pick a basis, and then you use the definite vector values, and you apply your equation using those values. And just like abstract vectors, abstract tensors allow to simplify calculation by condensing symbols, and also, not worrying about the components of the tensor until you actually need to make the calculations, the final calculations. And of course, that happens once you have chosen a basis for that. And just like vectors, they are independent of a choice of basis. And so that means that all equations using abstract tensors are valid in all frames of reference. And this is exactly what we want in relativity, for instance, and we'll see that in detail in another video of this series. Now, vectors are special cases. They only have one index, to specify which coordinate, for instance, you want to talk about. But tensors can have multiple indices, and they look like this, here. So this is a vector and this is a tensor. Now, as you can see, tensors can have both covariant and contravariant indices. In other words, upstairs and downstairs indices here, like this. And so they look a bit complex, but believe me, when you see something like that, that means they are hiding something much more complex than that, actually. Now, sometimes the tensor notation is used with indices, even for the abstract tensor, just to know it's a, PQ type. And so here is a definition again here. And let's see some example here. For instance, a 3-2 tensor T will map 3 linear forms, because 3 here, and 2 vectors to a scalar, okay? So its coordinates in that case would be expressed like this. And again, many mathematical objects can be considered as tensor. A scalar is a 0-0 tensor. A vector is a 1-0 tensor, and we'll see why on the next slide. The covector is a trivial example. It transforms a vector into a scalar, so it's a 0-1 tensor. A linear map would be a 1-1 tensor. A bilinear form, from V cross V to K is a 0-2 tensor, etc., etc. By applying tensor index rules, you can, again, really simplify some equations, with rules like this, that we saw before. Now, I said a vector is a 1-0 tensor. It should mean that a vector U of the vector space is a linear form from, the dual space to K, to the field of scalars. But it's actually a little bit more complicated than that. Any vector U can be associated by a map psi here, big psi, to a linear form like this, So that means to associate a linear form to the image of the vector by this linear form. And that means that this linear form is a member of the dual space of the vector space V. And psi is an injective map, which for now is not something we need to worry about. But if V is finite dimensional, as a finite dimension, then psi is an isomorphism. And thus, the vector U is isomorphic to the linear form psi U here, which by definition is a 1-0 tensor, from the set of linear maps to the field. On the other hand, if V has infinite dimension, well, its vectors are still 1-0 tensors, but that doesn't mean, unfortunately, that all 1-0 tensors are vectors of V. Note that there are other definitions of tensor, in particular using tensor product spaces with which all 1-0 tensors are vectors, even if V has infinite dimension. But these definitions involve a lot of other elements, and I prefer to use a simpler definition based on multilinear forms. An interesting example of tensor is a metric tensor. It's basically a bilinear form from V cross V, the vector space, to K. And therefore, you can consider that as a 0-2 tensor, And so it can be defined like this, obviously. Now, once the basis has been defined, it can be represented using tensor covariant coordinates like that. And there is also the contravariant version of the metric tensor. And in matrix representation, this particular one would be represented like this. This is assuming we are talking about a two-dimension space here. Now, it can also be applied to a single vector like that. And now there is an interesting thing happening here, that it will have the effect of lowering the index of the vector that you use here. And so transform the vector into a covector in the dual space. And that becomes a linear map from V to V star, which is a dual space of V. And so that's also something we can use in tensor equations to, when we need to lower indices or even to raise them if we use the contravariant part of a metric tensor. Here are some other examples of tensor operations. I'll let you have a look if you want to pause the video here. So to summarize, abstract tensors simplify calculations. Then you can choose a basis and do all the calculations with the elements of the tensor. All equations using abstract tensors are valid in all frames of reference, and that's really key for relativity. And they are pretty easy to work on, using simple rules to manage the indices. And finally, they can represent many kinds of linear objects, and therefore, in the same tensor equations, you can have scalars, vectors, linear forms, linear maps, etc., etc. And so all of this can be managed using tensors.